Hello everyone. Today I'll be presenting a case study on loan default probability. This is a project designed to assess the risk of default in vehicle loans using financial machine learning techniques. This presentation will cover the problem definition, model selection, feature engineering, class imbalance handling, and deployment process for predictive models that financial institutes can rely on to improve loan risk assessment. The primary objective of this project is to understand and predict loan default risk by analyzing borrower financial and demographic data. The target variable here is loan default, which signifies whether a loan was defaulted, allowing us to identify key factors associated with high risk borrowers. This project also underscores the importance of data driven lending decisions to enhance financial stability for lenders and accessibility for borrowers. While this project holds potential for accurate risk predictions, there are several challenges we need to address for effective model deployment. One significant challenge is balancing false positives and false negatives. False positives could wrongly restrict borrowers' access to credit, whereas false negatives might lead to financial losses. Additionally, borrowing behavior can evolve over time, necessitating periodic model updates. Privacy and compliance concerns also play a critical role as we handle sensitive borrowers' data. Feature engineering is a vital for enhancing a model's predictive accuracy. Using domain knowledge, we can develop a new features that reflect borrower behavior like loan to value ratios and delinquency patterns. By reducing the dataset's dimensionality, we can improve performance. Techniques like PCA and feature importance scores are tree-based models that help us select most relevant predictors, which is essential in managing computational efficiency and predicting accuracy. For this project, we explored various algorithms from baseline models like logistic regression to complex ensemble methods. The ensemble methods like random forest and gradient boosting are particularly effective in handling case imbalance, a common challenge in loan default datasets. Rather than focusing on accuracy alone, we prioritize metrics that address the imbalance such as recall precision and F1 score. The AUC ROC curve helps us evaluate the model's ability to differentiate defaulters from non-defaulters, with recall being our priority to reduce missed defaults. Since loan default cases are typically a small portion of the dataset, addressing class imbalance is crucial. Techniques like random undersampling and adaptive synthetic sampling helps us understand the model and make it more sensitive to defaults. While undersampling reduces the majority class, the addition focus on generating synthetic data for challenging samples, enhancing the model's focus on borderline default cases, which improves predictive accuracy. The final step is deploying the model into the production environment by integrating our best performance models such as random forest or gradient boosting. With loan processing system, we can make real-time predictions. Continuous monitoring allows us to track metrics like recall and precision, ensuring the model adapts to evolving economic conditions and borrower behavior. Regular retraining and feedback from loan officers keeps the model aligned with real-world dynamics, providing consistent support for the risk assessment. So now I'll be explaining the code behind this. Today I will take you through exploratory data analysis on loan default prediction dataset. Our goal is to understand the dataset better, examine patterns and uncover insights that help us building predictive models for loan default. So initially for the libraries and setup, we start by importing essential libraries like NumPy, Pandas, Seaborn and Matplotlib. We use OS to explore file structure and verify dataset location. Here we are working with something called train.csv. After loading the dataset, df.head provides a quick look at the first rows of the data structure, which involves all the columns listed in the dataset. And in df.info gives the data types and null counts. This is a crucial step to spot any missing values and understand the dataset's overall structure. Now for the numerical distribution columns, we'll be going to the analysis of what kind of charts we can use to predict the loan default probability. So for the distribution of numerical columns, to understand numerical columns we use histograms. These histograms reveal each feature's distribution. For example, we can see if the income or age are skewed. Such insights guide us on data pre-processing decisions like whether transformations are needed for modeling. We'll also be using a heat map to represent the relationships between features, and we plot a correlation matrix using a heat map. So here the heat map shows us how numerical values are related. High correlations between features suggest potential redundancy. For instance, if two features have a strong correlation, we might drop one or use a technique like PCA. This will help in improving the model's efficiency and avoid the overfitting. So now if we see here, we can take a look at the target variable loan defaults to see the data set is balanced between defaulters and non-defaulters. This count plot shows the balance between the loan defaulters and non-loan defaulters. If we find a significant imbalance, it could impact the model's prediction, requiring a resampling or class-wide strategies to prevent the model from favoring a majority class. So here if we see the next, we analyze the key called the categorical features, which includes employment type and perform CNS score description to see how each category of loan defaults. These normalized bar charts show the proportion of loan defaults within each category. For example, employment type might reveal the self-employed individuals having high default rate than salaried ones. Such patterns help in feature engineering as we can emphasize features that correlate with default. So after completing the EDA, we can have a better understanding of how the data handles the missing values, converting the categorical data into numerical formats, performing feature engineering and transformation. Finally, we will prepare the data for modeling, ensuring we split the training and testing sets for model evaluation. EDA is a crucial step that helps us uncover trends and relationships, guiding us in data preparation and model building. Through the visualization and correlation analysis, we gain insights into the data set, paving a way for an effective predictive model for loan defaults. In conclusion, by implementing this predictive model, financial institutes can achieve more informed loan disbursement decisions, enhancing both their risk management process and borrower accessibility. This model has a potential to reshape lending practices, making them more data driven and secure. Thank you for your attention, and I look forward to your questions.